In the previous video, I have solved homework for you, and there I have predicted that the value of beta will be 1 upon kT, where K is the Boltzmann constant and T is the absolute temperature. I have predicted it through physical arguments, and in the same video I have told you that I will derive it in the next lecture. So today's topic is derivation of beta equals to 1 by kT, or determination of the value of beta in the Boltzmann distribution law. Now the Boltzmann distribution law was derived in one of the earlier videos, which was Ni upon n equals to e to the power minus beta epsilon I upon summation over e to the power minus beta epsilon I. This is the famous Boltzmann distribution law. Now this summation over e to the power minus beta epsilon I is called the partition function. It is symbolized as F or Q. Let us use the symbol F. So Boltzmann distribution law can be rewritten as Ni upon n equals to 1 by F e to the power minus beta epsilon I. Now this beta is called the modulus of distribution. Let us first take logarithm on both sides. So we will have we take this n to the right hand side, so it will be Ni equals to n by F into e to the power minus beta epsilon I. Then we will take logarithm, so we will have ln Ni equals to ln n by F e to the power minus beta epsilon I. Then it will be ln n minus ln F plus ln e to the power minus beta epsilon I, or ln Ni equals to ln n minus ln F minus beta epsilon I. Now at equilibrium, both entropy and the thermodynamic probability attains maxima. And they are related as S equals to K ln omega, which I have derived earlier. This is the famous Boltzmann equation. Now S by K equals to ln omega. Now if we put the value of omega, which is n factorial upon product of n factorial, as I have discussed earlier, we will get after applying the Stirling's approximation. It will be n ln n minus summation over ni ln ni. Now we will put the value of ln I from equation 1. So it will be n ln n minus summation over ni, and it will be ln n minus ln f minus beta epsilon I. This is n ln n. Now this ln n will come out and summation over ni will be n. So we will get here n ln n for the first term. Now the second term will be positive and ln f will come out. So it will be n ln f. Summation over ni is n, total number of particles, and this will come out, it will be plus, beta will come out, and it will be summation over ni epsilon I, which is the total energy. Summation over ni epsilon I. So this is equals to total energy. So we get S upon K equals to, this will cancel, n ln f plus beta E. E is the total energy of the system, or S equals to nk ln f plus k beta E. Now we will differentiate this equation on both sides with respect to the total energy of the system. Now this k and n, these are constants, so it will come out and we will have the derivative of ln f. Here also k is constant, so k will come out and derivative will be applied on beta E. Now we express this in terms of beta. So we have to write here del beta del EV. Now here beta will come out, it will be the first part of the derivation, so it will be k beta, and then del E of E, that will be 1, so it will be k beta only. And the second term, here E will come out and we will have del E of beta. Now we will find the value of del F del beta. We know F equals to summation over e to the power minus beta epsilon I. So upon differentiating we will get del F del beta. Since derivative and summation commutes, we will have summation over this term. Now this will come out and derivative will operate on this parenthesis, so it will be del beta of minus beta epsilon I, so minus epsilon I will come out, and del beta of beta will be 1. So we have minus epsilon I e to the power minus beta epsilon I. Now from the Boltzmann distribution law, we have ni upon n equals to e to the power minus beta epsilon I upon f, the partition function, or e to the power minus beta epsilon I will be, we take this f to the left hand side, so it will be ni f upon n. Now we put this value in this equation, so we'll get del f del beta equals to minus epsilon I, and it will be ni f upon n. Now f and n are constants, it will come out, and we will have ni epsilon within the summation. So it will be minus f, now this is total energy, minus Fe upon n. This is the expression of del beta of the partition function. Now we will put this value in this equation. Here del beta of f, we have the value minus Fe upon n, minus Fe upon n. Now it will be nk upon f into minus Fe upon n. Then we have del E of beta plus k beta plus ke del E of beta. Now see, this f will cancel out, this nn will cancel out, so we will have now these two terms will cancel out, so we have del E of s to be k beta. Now this energy is the total energy of the system, and when it is purely the total energy, we can replace E by the internal energy U. So we can write del U of S equal to k beta. D cross Q equal to du plus D cross W. It will be D cross Q equal to du plus PdV, considering only mechanical work. Now at constant volume, this expansion work will be 0. So we will have D cross Q V equals to du. Now from second law of thermodynamics, we have ds equal to d cross q reversible by t. Now if we execute the process reversibly, we will have here d cross q reversible v equals to du. So from this we can write tds equals to du, or del S del U V equals to 1 by T. So we have del S del U V equal to K beta, and we have del S del U V equals to 1 by T. Now comparing these two equations, we can write k beta equals to 1 by t. Or beta will be equals to 1 upon kt. So what we have predicted is correct and we have derived it in this lecture. Now we can rewrite the Boltzmann distribution law as ni upon n equals to e to the power minus, we put the value of beta here, it will be epsilon I upon kt. Now the partition function, which is e to the power minus epsilon I upon kt over all levels, summation over all levels, in the case where there is no degeneracy. And if there is degeneracy, then this distribution law can be written as, this is the degeneracy factor, gi into e to the power minus epsilon I by kt and summation over gi into e to the power minus epsilon I upon kt. We will fill this distribution factor, the Boltzmann factor, in various cases like barometric distribution law, in chemical kinetics to find the rate, in vapor pressure. These are the examples which will associate the direct offshoot of this Boltzmann distribution law.